Okay, so we're going to run quickly through tangents and increasing and decreasing functions. So we have looked at some of this already in kind of the previous chapter, I suppose, or the previous videos looking at just calculus generally. So we're just going to look into it a little bit more detail, I suppose, now in terms of kind of applying it to functions questions and the questions we could be asked. So remembering kind of what we should already know, I suppose, heading into this is that the first derivative gives us the slope of the tangent of the curve. So that's kind of how we defined differentiation and the derivative of a function. And then finding the derivative at a particular point gives me the slope of the tangent at that point. Okay, so these are all things that kind of we should be familiar with already kind of heading in here. So I've drawn a little kind of diagram for us here as well of just that idea. So having the tangent at a particular point, and if I find the derivative or to find the equation of the tangent at that point, I could use the derivative to help me find the slope and then evaluate it at that point and use my equation of the line formula then. So I suppose the key thing there always being that to find the equation of a line, we need to have slope and we need to have a point on the line. So once we have those two things, we can find the equation fairly easily. So we're tying that together now with using calculus to find the slope as opposed to using, say, our slope function, for example. So the first example here, find the equation of the tangent to the curve at this particular point. So to find the equation, of a tangent or equation of a line, I need to have slope and I need to have a point. I have a point because I'm given this point here on the line. So I need to find the slope. To find the slope, I'm going to use the first derivative. So taking the first derivative of that, I get 12x squared plus 14x, and the last part there will be minus 6 over x squared. So that comes from this being 6 to the power of minus x to the power of minus 1, so minus 6x to the power of minus 2, which is minus 6 over x squared. Okay, so just doing that differentiation there. We want to find the slope at the point 114, so I'm going to take the x value of 1 and I'm going to sub that in. Okay, and that's going to give me 12 plus 14 minus 6, which is going to give me a value of 20. Okay, so I know the slope is 20. So the slope is 20 and my point is 114. So using my equation of the line formula, y minus y1 equals x minus x1. So y minus 14 equals 20x minus 20. So y equals 20x minus 6 as my equation of the line there. Okay, nice and straightforward in theory, I suppose. So we can also use that idea if we're given a particular slope and we want to find what point the line has that particular, or what tangent line would have the same kind of slope as that. So at what points on this curve is the tangent parallel to this particular line? So we have to take from this line, first of all, let's find the slope. So the slope here, we can use minus a over b, which will be minus 2 over minus 1, which of course is just 2. So I'm looking for points on the line which have a slope of 2. So let's find the kind of general equation, I suppose, for the slope of the tangents here. So 3x squared minus 10x minus 6. And I want to know at what points on my graph is this slope function going to be equal to 2. So for what points on the graph is the slope of the tangent equal to 2? So sorting that out gives me 3x squared minus 10x minus 8 equals to 0. If I factorize that there, I get 3x plus 2 and x minus 4. So I get x is equal to minus 2 over 3 and x is equal to 4. Now I was asked to find what points on the curve, so I need to sub back into y. So subbing back into y for the minus 2 over 3, first of all, minus 2 over 3 cubed, minus 5 times minus 2 over 3 squared, minus 6 times minus 2 over 3 plus 10. So let's use our calculator here. So making sure that I'm using brackets here as well so that my calculator can account for those in doing the powers. 2 over 3 squared minus 6 times minus 2 over 3 plus 10. Okay, and I get an answer of 310 over 27. Okay, for one of my y values there. Now I'm just making sure that I haven't made a little mistake somewhere along the way there. Minus 5x squared. No, okay, that's grand. And similarly here, then if I sub in for 4, So subbing in for 4 here, so 4 cubed minus 5 times 4 squared minus 6 times 4 plus 10. So that's going to give me, let's just sub in each one here. For 4, we're just going to change all of these out for 4. Same here again. Gives me an answer of minus 30. So the 2 points I have are the point minus 2 over 3, 10 over 27, and 4 minus 30. Okay, so we're going to jump into some exam questions here then on that, on finding the slope of the tangents then at particular points. The first one, find the slope of the tangent to the curve y equals x sine 1 over x when x is equal to 4 over pi. So here we're going to have to use a product rule, so letting my u be this part here, and I'm going to let v be this part here, those smaller. So u is equal to x, which means du dx is just 1. V is equal to sine 1 over x, which means dv dx is going to be cos 1 over x multiplied by minus 1 over x squared. Okay, the derivative of the angle part there. Okay, the derivative of my angle part, so it makes it a little bit longer for me. So minus 1 over x squared cos 1 over x. Okay, so we're finding the tangent of the curve, so dy dx is u dv dx plus v du dx. So that's x times minus 1 over x squared cos 1 over x plus v, so sine 1 over x du dx, then of course just 1. So I get minus 1 over x cos 1 over x plus sine 1 over x. Okay, so I need to sub in now when x is equal to 4 over pi. So making sure my calculator is in radians mode. So I'm subbing in here 4 over pi. Just making sure even here as well when I'm working with fractions that I make my fraction and then within my fraction I make another fraction, that I don't kind of just go and make all the fractions at the same time, because that can kind of lead to some issues then when you actually go to evaluate your fractions, the fractions there I should say. So making my fraction 4 over pi, and let's see what that takes me out with. An answer of approximately 0.151746. To 2 decimal places, we're getting 0.15. Okay, 0.15. So the slope of the tangent to the curve at that point is approximately 0.15. Let's look at another example here. So let f of x be equal to 2x over x plus 2. Find the coordinates at the points at which the slope of the tangent to the curve is 1 over 4. So what they're saying here is find the coordinates of the points at which the slope is equal to this. So they're saying that the derivative, or the slope, is equal to a quarter. So we have to find the values for which that is the case. So again, we're going to be differentiating. So we need to use one of our rules here. This is going to be a quotient rule because we have one expression divided by another. So if u is 2x, then du dx is just going to be 2. And similarly then, if we let v be equal to x plus 2, then dv dx is just going to be 1. Okay, my quotient rule then dy dx is v du dx minus u dv dx all over v squared. And again, that rule is in our formula and tables book, so we don't necessarily need to know it off by heart like that. By 2x minus u, which is, or sorry, not u, 2x, just 2 there, minus u, which is 2x by dv dx, which is just 1, all over v squared, which is x plus 2 squared. So we get 2x plus 4 minus 2x all over x plus 2 all squared. So that breaks down to 4 over x plus 2 all squared. And I want to know now, where is dy dx equal to a quarter? So remembering dy dx is 4 over x plus 2 all squared. So doing some cross multiplication here and getting x plus 2 all squared is equal to 16. Okay, so now I need to evaluate this function. So I'll multiply out my brackets here. Equals 16. I get x squared plus 4x minus 12 equals 0. So two numbers that will multiply to give me 12 but add to give me 4. So I'm looking at x plus 6 and x minus 2. So I get x is equal to minus 6 and x is equal to 2. Now I'm asked to find the coordinates of those points, so I need to sub those back into the original function. So if I do f of minus 6, I'll just use my calculator to evaluate that one. So let's try that there. So minus 6 over minus 6 plus 2, that's going to give me 3. If I do f of 2, so the same idea again, but this time we'll just sub in for 2, and I get 1. So my 2 points are minus 6, 3, and the point 2, 1. That's my 2 points there, where my graph will have that exact slope. Okay, we have one more question to look at in this kind of part. So h of x is equal to cos 2x. A tangent is drawn to the graph at the point where x is equal to pi over 3. Find the angle that this tangent makes with the positive sense of the x-axis. Okay, so we're going to work out first of all and evaluate the derivative here to get the exact slope of this tangent. So the derivative here, I'm going to differentiate the angle part or the function part, and I also need to differentiate the angle part. So my function part, my cos 2x, is going to go to minus sine 2x, and I need to then multiply by the derivative of the angle, which is 2. So I get minus 2 sine 2x. I want to find the slope. So I want to find the slope at x equals pi over 3. So let's evaluate that. So I'm doing the derivative of evaluated at pi over 3 sine 2 pi over 3. And if I work that out here, it's minus 2 sine pi over 3. Evaluated there, and I get an answer of minus root 3. Get an answer of minus root 3. Okay. So essentially what we're saying here is that at this point, the slope that I have, okay, the slope that I'm getting here for this particular tangent is that it has a slope of minus root 3. It has a slope of minus root 3. And if we remember kind of from our coordinate geometry, or kind of what we're looking at here, we have a line. If this is my x-axis, so this is y equals 0, this is my x-axis. And what's happening is I have a tangent that's making a particular angle with the positive sense of the x-axis here. So essentially what we're working with is if we work out our reference angle using this side here. So I'm saying that tan theta is minus root 3. Okay, so tan theta, the angle that I'm making with the sense of the x-axis, or the kind of slope that I have there, is tan theta. So I want to work out what that value could be. So I'm kind of looking at where is tan negative, things like that. So I'm just going to take the positive value here. So I'm going to take the positive value for that. So tan of my reference angle is root 3, which will tell me that my reference angle is tan inverse of root 3, which is pi over 3. Which is pi over 3. So this angle here is pi over 3. Now I want the angle that it makes with the positive sense of the x-axis, so that's going to be this part here. So that's going to be pi, take away pi over 3, which is 2 pi over 3. That's my answer there. So therefore, the tangent makes an angle of 2 pi over 3 with the positive x-axis, with the positive x-axis there. Okay, so just remembering kind of the general idea that we have there, relating that back to our coordinate geometry as well when we're looking at slopes of lines and things like that, and bits of trigonometry coming in there as well, I suppose, with your tan, your kind of solving your equations in that regard there. So a few different elements, if you like, coming into that part. Let's just move on then to the increasing and the decreasing functions. So we've looked at maybe a little bit before, or kind of have thought about, but we're just making it a bit more explicit here. When a curve is increasing, the derivative will be greater than 0. When a curve is decreasing, the derivative will be less than 0. So when it's increasing, the rate of change is positive. It means that the y values are increasing as the x values are increasing. So in theory, if we think about a line, that just means that the line is going up like that my curve is going up like that. When it's decreasing, the y values are going down as the x values are going up as we go across with my x values. So in terms of these rates of change, we're always kind of talking about when x is increasing, what's happening to y, how is y changing. So for what values of x is this function increasing? So increasing to me says derivative greater than 0. So I need to find the derivative first of all. So let's use the notation they have used. We'll call it g dash x. So 3x squared minus 2x minus 8, and I want that to be greater than 0. Okay, so I want that answer to be greater than 0. I'm going to let it equal to 0 first of all and solve the equation to find the two roots of this function to find out where it is 0. And that's going to give me 3x plus 2 and x minus 2. I'm just going to jump straight to some answers there. So we get x equals minus 2 over 3 and x equals 2. So if I was to sketch this out, what I'm working with is I have a graph, something like this, where my two roots are 2 and minus 2 over 3. Now I want to know where is this function greater than 0, so I'm looking at the points where the function is above the x-axis, where it has y values that are bigger than 0. So that's above the x-axis. So that's for the two kind of outer ranges there. So we're looking when x is less than minus 2 over 3 and when x is greater than 2. So for both of those, my function will be increasing. My original function will be increasing because for those values, my derivative is positive. So that's kind of the idea. We're tying back now to our algebra 3, to our inequalities, to our quadratic inequalities there. To the next one, prove that the curve is decreasing for all x. So decreasing means that my derivative is negative. So I need to show that the derivative is going to be negative for all values of x. So let's find the derivative first of all. So we get minus 6x squared plus 12x minus 6. Okay, I want to show that this is always negative. I'm going to factor out a minus 6 and I get x squared plus 2x, or sorry, minus 2x, x squared minus 2x plus 1. I should hopefully recognize this as being a perfect square, which means that I can rewrite it as x minus 1 all squared. So that's the same as the quadratic that I have there. It's a quadratic with a repeated root at 1, so I can factorize it in that way. If you don't remember it's a perfect square, you could just kind of attempt to factorize it, and you should end up with the same bracket repeated twice. But what this means for us here is the minus 6 is always negative. This part here will always be positive. So overall, it's going to always be negative. Because it's minus 6 multiplied by something that's always positive, then that means it's always going to be decreasing. So it's always going to be negative. So therefore decreasing for all x. Therefore it's decreasing for all x. So you can see there now, proving that it's increasing and decreasing. Again, we're coming back to the inequality proofs that we would have done in algebra 3. So important to kind of brush up on those as well. Being able to prove that a function is always decreasing or always increasing. And a lot of the time that's using perfect squares. It's using completing the square. It's using all these different kind of techniques that we have. So just making sure that we're kind of fluent enough with those. Let's just look. I think we only have maybe 1 or 2 exam questions here to look at. So let's show that this function is decreasing at c. So to show that it's decreasing at c, that's going to mean that the derivative is less than 0. So first of all, of course, we have to find the derivative. Now, a bit of a complicated looking function here, but I'm noting that it's e to the power of something, and I know that when I'm differentiating exponential functions like that with base e, that the function itself isn't going to change. I just need to watch out for the powers here up the top. So when I differentiate, I'm going to have 1 root 2 pi. I'm going to have e minus a half x squared. So everything's staying the same there, but I'm going to multiply by the derivative of the top part, which is just a minus x. Okay, which is just a minus x. Yeah, just a minus x. Okay, so continuing on, then we can right, minus x over 2 pi e to the power of minus half x squared. So at C, which is the point 1 over root 2 pi e, I'm just focusing on the 1 part because that's the x value. So I get minus 1 over root 2 pi e to the power of minus a half times 1 squared, which is going to be minus 1 over root 2 pi e to the power of minus a half. Okay, and I can take all that down. Okay, so I can bring all of that down with me to get minus 1 over root 2 pi, and I'm going to take the e underneath as well. So remembering as well, e to the power of half, same as a square root, so I can actually bring that e down and I can combine it to the square root function there. Because that's always negative, the 2 root e part is always going to be positive, so the minus at front is going to tell me that it's always less than 0. So therefore, or for that particular value, it's less than 0. So therefore we know the function is decreasing at C. So therefore my function is going to be decreasing at C. Okay, so again, just making sure that we're kind of following through with all of those points there. Looking then at the last function, this is going to use a little bit of trigonometry and trig identities for us here. So first of all, finding the derivative of this function here. So the 8x goes to 8, the sine 4x goes to cos 4x, and we have to multiply by the 4. And the 4 sine x then is going to go to 4 cos 2x. And then again multiply by 2, so I get 8 plus 4 cos 4x plus 8 cos 2x. To express the derivative in terms of cos 2x, I'm going to need to make use of some trig identities here. Okay, so I need to make use of some trig identities. So I want to express everything in terms of cos 2x. Now at the minute I have the 8 cos 2x, so that's fine, but that's obviously not exactly what I want to have. The problem here is the cos 4x. Okay, that's kind of the problem. The cos 2x, grand, it's the cos 4x we need to worry about a little bit. So I'm going to make use of the first identity, which is that cos 2x is the same as cos squared x minus sine squared x. So if we adapt that for our question here, we can kind of deduce then that cos 4x is the same as cos squared 2x minus sine squared 2x. Okay, so again, that's going to help me now that I'm going to be able to write the cos 4x as cos squared 2x minus sine squared 2x. However, then I'm bringing in a sine, and I don't really want to have sine either. So we're going to make use of the fact that sine squared 2x plus cos squared 2x would be equal to 1. Which means then that sine squared 2x is equal to 1 minus cos squared 2x. So combining kind of both of these, so instead of sine squared 2x, I'm going to be putting in this idea here. So combining those together now, cos 4x can be rewritten as cos squared 2x minus 1 minus cos squared 2x, which is going to give me cos squared 2x minus 1 plus cos squared 2x, which is of course 2 cos squared 2x minus 1. So substituting now that back in for the cos 4x that I have at the top, I get that the derivative is 8 plus 4 times this, so 8 cos squared 2x minus 4 plus 8 cos 2x, which is going to give me an answer of 4 plus 8 cos squared 2x here, 8 cos squared 2x plus 8 cos 2x. So a lot of kind of manipulation and trig identities being used. There are two identities being used to manipulate it in terms of what they want. Cos squared 2x is considered in terms of cos 2x because we can remember that cos squared 2x is the same as me writing cos 2x all squared. Okay, so we know that kind of identity already. Now to prove that this is increasing, we need to prove that this derivative is greater than 0 for all x. So we'll write out the derivative there again. I'm just going to manipulate it a little bit. So I'm going to write the cos squared 2x first, plus 8 cos 2x plus 4. Okay, and I want to show that this is always going to be positive. Now, looking at the question that I have here, it's kind of reminiscent to some extent of a quadratic, really, because I have a squared part, a normal part, and then a number at the end. Okay, so it's kind of reminding me of a quadratic. To prove that's increasing, I'm generally thinking perfect squares, or indeed completing the square then. So I'm going to have to complete the square here, so I'll take out 8, take out a factor of 8, so I get cos squared 2x, and maybe just to make it clearer here, I'll write this out with the squared on the outside, cos 2x here, and this is going to be half. When I'm completing the square, I take the coefficient of the x part, which is 1, and I divide it by 2, and then I'm going to square it to get a quarter. So I have cos 2x squared plus cos 2x plus a half. I'm going to be adding a quarter, and I'm going to be subtracting a quarter also. So remember, we add and subtract the same amount to the question because we can only change the question by doing that, I suppose. So now adjusting my question here, I have cos 2x squared plus cos 2x. I'm going to bring that quarter over as part of this kind of first part of the equation, and then I have the half minus a quarter on the end here. So taking now this part here, this is my perfect square part, and hopefully we remember as well that when you're rewriting that perfect square, you can rewrite it as using the part that we had over on the right hand side here. So when I divided the coefficient by 2, that's going to be the part that ends up in our bracket part there. So we're going to end up with the little kind of the half part there, I suppose, to give us the exact answer we have at the end, and it's going to be minus a half here. I want to show that this is greater than 0, and then I'm just multiplying by 8. So 8 cos 2x plus a half squared minus 4 is greater than 0. Okay, and I want to prove that this is always going to be, oh, excuse me, sorry, that should be, this part here should be a quarter, a half take away a quarter. Let's use my calculator, seeing as I can't do it myself. A half take away a quarter, of course, is just a quarter. So this part here should just be plus 2 instead of plus 4 there. Plus 2. And what we can say looking at that is that this is always positive, and this part is also always positive. So therefore, it's all always positive. So therefore, the function f of x is always increasing. That's the general idea. Okay, so just important to make sure that, I suppose, looking at what we've seen across these questions here is revising your inequalities, revising your inequality proofs, revising here now as well. You're being able to completing the square, the perfect squares, all of those ideas. So it's not just enough to, I suppose, know like, oh, derivative has to be greater than 0. Sometimes you have to be able to prove that as well, and knowing when to sub in the question, knowing how to find the equations of the line. So even though, yes, the actual kind of base level of what we need to know in this section is small enough, there's a lot of different parts that can be pulled into it as well. So just being aware of kind of all of those different aspects.